Here we discuss certain types of Riemann integrable functions. First we will see if f from AB to R is continuous on closed interval AB, then f is Riemann integrable, or otherwise we say f belongs to RAB. So let us try to prove this. This theorem says that every continuous function defined on a closed and bounded interval is Riemann integrable. Let us try to prove this. For proving this Riemann integrability of the continuous function, we use the idea that for every epsilon positive, we will find two step functions alpha epsilon and omega epsilon with the property that alpha epsilon x is less than or equal to f of x less than or equal to omega epsilon x, and integral a to b omega epsilon minus alpha epsilon is less than epsilon. Then we know by one theorem this function is Riemann integrable. A function is Riemann integrable if there exist two step functions alpha epsilon and omega epsilon for every epsilon. If we can find satisfying these two conditions, then we can assure that the function is Riemann integrable. So how to find this alpha epsilon and omega epsilon corresponding to an epsilon greater than 0 taken? So let's start with an epsilon greater than 0. Let epsilon greater than 0 be given. Now since the function defined on closed interval AB is continuous, since f from AB to R is continuous, by uniform continuity theorem, f is uniformly continuous on AB. That is, every continuous function defined on closed and bounded interval is uniformly continuous. Therefore, by the definition of uniform continuity, for this epsilon positive, there exists a delta positive such that modulus of fx minus fy is less than epsilon for all xy in AB, satisfying modulus of x minus y less than delta. You take this in equation 1. Now, in addition to this, let us assume that this mod of fx minus fy is less than epsilon divided by b minus a. So, f is uniformly continuous. Then we are getting the condition that there exists a delta such that mod of fx minus fy is less than epsilon by b minus a for all xy satisfying with mod of x minus y less than delta. Now, let P be any tagged partition. It's a partition of. Let P be any partition of closed interval AB with the norm P less than delta. So we have a partition now of AB, say x0, a equal to x0, x1, x2, etc., xn minus 1, xn, so xk minus 1, xk, finally xn is equal to be a partition. Here each modulus of xi minus xi minus 1 is clearly less than delta, because we assumed norm p is less than delta. Now, since f is continuous on AB, it is continuous on each subinterval xi minus 1 xi. This xi minus 1, xi minus xi minus. So interval is xi minus 1 xi. It is continuous on each xi minus 1 xi for any I is equal to 1 to etc. n. And therefore, by boundedness theorem, maximum minimum theorem, f has absolute maximum and absolute minimum in interval xi minus 1 xi. F has absolute maximum and absolute minimum on each interval xi minus 1 xi. So it is something like this. Suppose this is the interval that we are getting, xi minus 1 xi, and suppose this is the part of the curve in the interval xi minus 1 xi, then the function may have maximum at the point u, minimum at the point u and maximum at the point v. So there exists actually u and v, say ui and va in xi minus 1 xi such that f of ui is minimum and f of vi is the maximum on xi minus 1 xi. Now we are in a position to define two step functions alpha and omega. Now define alpha epsilon x is equal to f of ui for x in xi minus 1 xi and omega epsilon x is equal to f of vi for every x in xi minus 1 xi. Clearly, alpha epsilon and omega epsilon are step functions, and this is defined for all y I equal to 1 to etc. n. Then alpha epsilon and omega epsilon are clearly step functions with the property that alpha epsilon x is less than or equal to fx less than or equal to omega epsilon x, since for every x in xi minus 1 xi, f of ui is less than or equal to f of x is less than or equal to f of vi for all x in the interval xi minus 1 xi. So first we got the condition of alpha epsilon and omega epsilon. Now let us try to find integral a to b omega epsilon minus alpha epsilon. We want it less than epsilon, which is equal to integral a to b omega epsilon minus integral a to b alpha epsilon is equal to By the definition of Riemann integral of a step function which takes the values f of v1, fv2, etc., fvn, integral a to b omega epsilon is sigma I is equal to 1 to n f of vi delta xi, where delta xi is xi minus xi minus 1 minus integral a to b. Similarly, alpha epsilon is f of ui delta xi. So this is equal to sigma I is equal to 1 to n f of vi minus f of ui the whole into delta xi. Since ui and vi belong to ui and vi belong to the same xi minus 1 xi whose length is less than delta, by 1 we have modulus of f of ui minus f of vi, or f of vi minus f of ui is less than epsilon by v minus a by the condition of uniform continuity. And therefore, this is clearly less than sigma I is equal to 1 to n epsilon divided by b minus a into delta xi by 1. By 1. This is actually 2. Let us take. So, by 1 means the condition of uniform continuity. And it is equal to, you can take epsilon by b minus a outside, sigma is equal to 1 to n delta xi, and sigma is equal to 1 to n delta xi is the total length which is b minus a of the interval ab. Sigma delta xi means equal to the length of the interval ab, b minus a. So we have got integral a to b omega epsilon minus alpha epsilon is less than epsilon. So this is the third equation. In equation, there is a second condition of alpha epsilon and omega epsilon. Thus, we have two functions, step functions, alpha epsilon and omega epsilon, satisfying the conditions alpha epsilon x less than or equal to fx less than or equal to omega epsilon x, and integral a to b omega epsilon minus alpha epsilon is less than epsilon. And therefore, by sandwich theorem, f belongs to RAB. F is Riemann integrable. Thus, every continuous function defined on closed interval AB is Riemann integrable on AB. The next class of Riemann integral functions are monotonic functions. So that is the next result. If f belongs to RAB, sorry, f from AB to R is a monotonic function, if f from AB to R is monotonic on closed interval AB, then f belongs to RAB. That is, every monotonically increasing or decreasing function on closed interval AB is Riemann integrable. So the proof is done by the same way as we proved a continuous function is Riemann integrable with the help of two step functions. Here also we will use the same Skews theorem for proving the function is Riemann integrable. For that, you have to identify two step functions omega and alpha satisfy the two conditions of Skews theorem. Given f is monotonic, so let us assume that f is monotonically increasing for the time. Let f be monotonically increasing on closed interval AB. Now divide or partition the interval AB into n equal subintervals, say xi minus 1 xi, I is equal to 1, 2, etc. n, such that xi minus 1 is equal to b minus a divided by n. So, if you draw the picture, it is somewhat like this. This is x naught, this is x1, suppose this is some xi minus 1, and this is xi, and this is xn. So, the function is monotonically increasing. So, this is the interval xi minus 1 xi. Since f is increasing on each subinterval xi minus 1 xi, let us define two step functions alpha and omega, such that alpha of x is equal to f of xi minus 1, that is the value of the function that left endpoint of the interval xi minus 1 xi, and omega x is equal to f of xi for every x in the interval xi minus 1 xi, and this is done for all I is equal to 1 to etc. n. Clearly, alpha x is less than or equal to f of x is less than or equal to omega x. And we have to verify the second condition of this alpha and omega, that is integral a to b omega minus alpha. Integral a to b omega equal to, by the definition, sigma I is equal to 1 to n f of xi minus 1, sorry, f of xi, omega it is f of xi delta xi, I is equal to 1 to n, which is equal to sigma I is equal to 1 to n, and delta xi we have taken as b minus a divided by n. This is actually delta xi. So, f of xi into b minus a divided by n, number 2, and integral a to b alpha is equal to sigma I is equal to 1 to n f of xi minus 1 delta xi, which is equal to sigma I is equal to 1 to n f of xi minus 1, again delta xi is b minus a divided by n, and therefore using 2 and 3, integral a to b omega minus integral a to b alpha is equal to sigma I is equal to 1 to n f of xi minus f of xi minus 1 into b minus a divided by n, that is integral a to b omega minus alpha is equal to b minus a by n, you can take outside. sigma I is equal to 1 to n f of xi minus f of xi minus 1. That's equal to b minus a divided by n into, if you expand this summation, you can see that this is f of x1 minus f of x0 plus f of x2 minus f of x1 plus etc. plus f of xn minus f of xn minus 1. Cancelling, say telescopic sum, so cancelling f of x1 plus minus f of x1 and minus f of x1 like that, you will get inside there are only fxn minus fx0, which is equal to b minus a divided by n into fb minus fa. Now, had we chosen this n very large for a given epsilon positive, such that n is greater than b minus a divided by b minus a into fb minus fa divided by n is less than epsilon, such that b minus a by n into fb minus fa is less than epsilon, then we would get integral a to be omega minus alpha is less than epsilon. Number 2. The second property that we have to satisfy for alpha and omega, that will be 4. So 1 and 4 say that for a given epsilon positive, there exists a partition P of AB, and there exist two step functions alpha and omega, such that alpha x is less than or equal to fx is less than or equal to omega x by indication 1, and integral a to b omega minus alpha is less than epsilon, the indication 4. Therefore, again by Squeeze theorem, f belongs to R alpha, R AB. F belongs to R AB. Thus, every monotonically increasing function defined on closed interval AB is also Riemann integrable. Here we have taken up increasing. Similarly, for decreasing also we can prove the same result.